Ever wondered how your phone figures out the absolute fastest delivery route? Or how an AI model learns to tell the difference between a cat and a dog? Well, behind all of that magic is a powerful idea called optimization. But here's the kicker. It's not just one idea. It's actually two completely different worlds. One is a world of perfect certainty, where you're guaranteed to find the best answer. The other, well, it's a whole lot messier, kind of like reality itself. So let's dive in and see what that really means. At the end of the day, every single optimization problem is trying to answer this one simple question. Out of all the choices, all the possibilities, which one is the absolute best? It sounds so straightforward, right? But how we go about finding that answer, well, that changes everything.
And, this isn't some abstract theoretical thing. Optimization is the invisible engine running so much of our world. It's humming away behind the scenes in financial models on Wall Street, in logistics that get your packages to you, and in the very way we train the AI that's becoming a part of our daily lives.
Okay, so let's get a little more specific about this search for the best. How do we actually set one of these problems up? It turns out no matter how ridiculously complex an optimization problem might seem, you can always break it down into three basic parts.
First up, you've got your decision variables. Just think of these as all the different knobs and levers you're allowed to play with. Second, there's the objective function. That's the one single number you're trying to either maximize or minimize. Like minimizing cost or maximizing profit. And finally, you have constraints. These are the hard and fast rules you absolutely cannot break, like the budget you have to work with or the amount of time you have.
All right, let's step into the first world. This is the world of convex optimization. And honestly, the best way to picture it is as a single, perfect, incredibly smooth bowl. It's just elegant, it's predictable, and from a math perspective, it's beautiful. So, what actually makes a problem convex? Well, it all comes down to this really simple visual idea. Imagine you pick any 2 points on the surface of our bowl, anywhere at all. Now draw a straight line between them. In a convex function, that line will never, ever dip below the surface of the bowl. There are no bumps, no hidden valleys, no tricky spots. It's just one smooth, perfect curve. And this simple shape gives convex optimization a kind of superpower. It's captured perfectly in this one phrase. It means that if you were to drop a marble anywhere on the side of this bowl, it doesn't matter where you start, it's always going to roll down and settle at the very bottom. Any low point you find is the lowest possible point. There are no tricks, no false bottoms. This guarantee is what makes the convex world so incredibly powerful. Our algorithms aren't just guessing or hoping they find the best answer. They are mathematically guaranteed to find it. The whole process is super efficient, the outcome is predictable, and there are absolutely no hidden traps or nasty surprises. It's just this perfect, well-behaved world.
But here's the thing. Most of the real world doesn't look like a perfect bowl. Not even close. It looks a lot more like this. A huge, rugged mountain range, packed with peaks, countless valleys, and all sorts of treacherous terrain. Welcome to the other world, the world of non-convex optimization.
I mean, the difference is just night and day, right? Instead of that one smooth bowl, we've got this wild, unpredictable landscape. Instead of one single bottom, there are tons of local minima. Dozens, maybe thousands of little valleys, all at different depths. Finding your way down the bowl is easy. Trying to navigate a mountain range in the fog, that's really, really hard, and the outcome is completely uncertain. The journey through this landscape is just perilous for an algorithm. It can easily roll down into one of these many valleys and get stuck, thinking it's found the bottom, when the real lowest point is a whole mountain range away. And even worse are these things called saddle points. They're these sneaky, almost flat areas where an algorithm might just stop, totally fooled into thinking its job is done. So finding an answer is easy, but knowing if it's the absolute best answer, that's incredibly difficult. So you might be wondering, why on earth do we even bother with this messy, unpredictable world? The answer is simple, because this is where reality lives. From designing a complex jet engine to training the most powerful AI models, the problems that really define our modern world are almost all non-convex. They're just inherently rugged and complex.
And you know, there is no better place to see these two worlds smash right into each other than on the battleground of artificial intelligence. Machine learning gives us a perfect example of how both the perfect bowl and the rugged mountains are being used every single day.
So on one side, you have a pretty simple model like linear regression. Its whole job is to find the best possible straight line through a bunch of data points. And the thing it's trying to minimize, its loss function, it's a perfect convex bowl. We are guaranteed to find the one single best answer every time. But on the other side, deep neural networks, their loss functions are ridiculously non-convex. We're talking a massive high-dimensional mountain range. We have absolutely no guarantee of finding the best solution. But by exploring this crazy complex landscape, they achieve incredible expressive power that the simpler models just can't touch. And that brings us to the core of it all, the ultimate trade-off. Choosing between these two worlds isn't really about which one is better. It's about what you need to prioritize. Do you need the certainty of a perfect answer, or do you need the power to model a messy, complicated reality?
Let's just break it down. With convex problems, you get that ironclad guarantee of finding the best solution. The algorithms are efficient, they're straightforward, but their ability to model the really complex stuff in the world can be kind of limited. Now, non-convex problems, they offer zero guarantees. They can be incredibly expensive and complicated to solve. But the reward for all that trouble? They are so much more expressive for modeling the complex systems we actually care about.
So what this really means is that when we decide to step into that non-convex world, we're making a very deliberate choice. We are knowingly trading away the absolute guarantee of a perfect solution in exchange for the power and the flexibility we need to model the world as it truly is, in all its messy glory.
And that kind of leaves us with one final thought to chew on. When you're facing problems that are as intricate and messy as our own world, what do you value more? Is a provably perfect answer to a simplified version of the problem better than a good enough but really useful answer to the real thing? The choice between these two worlds, it's a choice we're making all the time.